Sydney, if you for some reason see that go out, just put that again. You shouldn't.
Okay.
Finally, I made it home safe.
Anybody send any emails about this room being too small? Nobody? Can you hit the four corners on those light switches, get all the lights on? Yeah, thank you.
Okay. Top right. You mean the left? That says camera.
All right.
I think.
Any questions at all about the homework? Anything?
Yeah.
Any questions about the homework? 6, 7, 6 point. Wait, you did 6, 7.
But we didn't. I had some weird. The magnitudes when I calculated the H fields wasn't working out when I did it.
All right, we'll go through it kind of fast. This is 6.7. I think we did that one. The magnitude of the H field. That's just E over A, right?
I'm just saying something different from the book.
All right, well, we'll settle that. All right. This is problem 6.7 that I think we did, and he gave us an E field. Go ahead, I don't know. Anybody?
It's E x y t is equal to 5 cosine pi to the 6 t minus 3x.
5 times 10 to the 6t, right? Right?
Minus 3x plus 2y in the AZ direction.
All right, is it in the air?
It doesn't specify.
All right, here's how we can figure it out. And I want you to watch this, guys. So I'm going to go from this domain, I'm going to go to the phase domain. Now, you all see that omega is the coefficient of t. So I can write omega is equal to pi times 10 to the 6. And that means f is really omega over 2 pi, right? So that means this is 1/2 times 10 to the 6th, or really 5 times 10 to the 5th hertz. Y'all follow me on what I'm doing here? Can everybody see this okay? Y'all understand what I'm doing? I'm just getting the value of omega. Now I'm going to take this and put it into the phasor domain. So that means the E field itself is going to be 5, and it's just going to be e to the minus j, and then it's going to be 3x minus 2y az. Now the reason I did this is I want the minus j there because I know whatever this coefficient is going to be actually beta times the direction of propagation. Y'all follow me on this? How many see this right now? Gotta make sure. Far back, y'all with me? Okay. Now what I did last time is I said I'll factor out, first I get actual value of beta in magnitude. It's just going to be the square root of the coefficients of x, which is 3 squared, plus the coefficients of y, 2 squared. So it's equal to the square root of 9 plus 4, or 13. That's the magnitude. And that means I can get the E field itself equal to 5 e to the minus j, and then I can take the magnitude down, the square root of 13 here, and I have 3 over the square root of 13 x minus 2 over the square root of 13 y in the AZ direction. Now, I'm going to figure out something about this, and the way I'm doing this problem, and I'm moving a little quick because we did this last time. I wanted to get to where I was last time. Y'all remember this? Now, one of the things we can find out is what, in fact, material we're in. Now, you didn't see any e to the minus alpha z. Y'all with me? That means it's lossless. That means you can state right away sigma is 0 for this one. Follow me on this, everyone? Now, next we're gonna figure out what the actual phase velocity is. Phase velocity is omega over beta. Y'all agree with that? Now, we better be less than speed of light, or this problem makes no sense. All right? Follow me on this? So we've got omega over there, pi times 10 to the 6th, and we have beta over here, square root of 13. So what's the value of V phase? Anyone? Is this what you were doing, by the way?
Is the time domain
Well, did you do this part?
I used the
Never mind. Just give me that. I'm very curious because I have a feeling this is a Whitworth problem that's got there's a mistake made, but he didn't catch it, I think. Let's see. Because this is a very small phase velocity. This is going to be what? About 10 to the 6th, 10 to the 5th? What's the speed of light? 3 times 10 to the 8. 2 orders of magnitude less. Do you know what kind of epsilon relative that is? That's enormous. What is it?
It's 8.7 times 10 to the 8.
All right, 8.7 times 10 to the 5th hertz, right? It's lossless. Do y'all agree with that? Now just watch how crazy this is. So let's figure out what kind of material we're going through. Well, we know that phase velocity is also equal to what? If it's lossless, it's what? 1 over the square root of mu epsilon. Are you with me? If it's lossless. Y'all remember me doing this? Okay. Now, this breaks out as what? 1 over the square root of mu naught epsilon naught times 1 over the square root of mu relative epsilon relative. Now, does it say it's non-magnetic anywhere in that problem?
It doesn't say it, but in the solutions it says most of it.
All right, then I'll assume it's non-magnetic. So that means it's just this, right? All right, what is that? 1 over the square root of mu naught epsilon naught is the speed of light, right? 3 times 10 to the 8 over the square root of epsilon relative is equal to the phase velocity, is equal to this. 8.7 times 10 to the 5th. Now, what does that mean epsilon relative is? Y'all follow me on what I'm about to do? I'm going to divide both sides by 8.7 times 10 to the 5th, then multiply by epsilon square root of epsilon relative, then square that. So that means this is going to be 3 times 10 to the 8 over 8.7 times 10 to the 5th squared. Give me that value. It's massive. I mean, this is like something you can't even make. I don't think exotic materials can get this big.
1.1 times
10 to the 5th. You know if any material comes close to that? I don't. Maybe the center of a black hole or something, you could make an argument for that. But this is insane. He made a mistake. All right. So now if we carried out the logic here, I'm going to show you how crazy it gets. If that's our epsilon relative, what's our value of eta naught? Well, our eta. Eta is what? Square root is lossless, so just mu over epsilon, right? Y'all follow me, class? All right, so we can say this is equal to the square root of mu naught over epsilon naught times what? If he said it's non-magnetic, 1 over the square root of epsilon relative, right? Let's take a look at this. So this square root of mu naught over epsilon naught is what? It's 120 pi, right? It's free space impedance, right? 120 pi over the square root of 1.1 times 10 to the 5th. So what do you get for the impedance of that? 1.1 ohms. That's a little small for a lossless medium. Now, for metals, you can easily have impedances that are way down there, 0.0001 ohms, all right? But for a lossless material to have that kind of impedance, intrinsic impedance, that's insane. So the H field you should get for this one. Now, I know what Whitworth did. what he did is take the curl of, I think I did at least, he took the curl of E, and he said it's equal to minus J omega mu times H, and he let this be mu naught. So then he took this, and he simply divided by, really, omega, mu naught, and J, to get, the minus sign there, to get his value of H. That's what he did. But what he forgot to do is make sure the problem was logical and made sense. This will not get you the same value I'm about to show you. This is the right value. If that's the impedance, then the actual value of the H field, how do we get it? Remember, this is a plane wave propagation. Right, we use that trick. H is equal to 1 over eta, and it's lossless. Unit vector in the direction of propagation crossed into the E field. Well, the direction of propagation for this one, it's a little odd, because how do you get that direction of propagation? It's really this. That is AP right there. Only put, I'll write it down for you. That's going to be a unit vector in the direction of propagation for this one. It's simply going to be that term, and it won't be x, it'll be ax, so it's going to be 3 over the square root of 13 ax minus 2 over square root of 13 ay. And you can check that, the magnitude of that is 1, that is a vector in the direction of propagation, a unit vector. Do you all agree with this? So to get this, technically, I should say it's going to be equal to 1 over eta, 1.1, almost 1. Unit vector in the direction of propagation, which is this. And then I have to take that and I have to cross it into the E field. Phasor E field right here. Now I'm just going to put it down like this. Crossed into 5, and we're just going to leave it as e to the minus j beta dot z dot. And just leave it like that for now, az, because the cross product only is going to be, this term is going to be the same thing as this coefficient here of e to the j minus j beta z, or this. Y'all with me? So follow me on this. When you do the cross product, what do you end up getting for this? Take a good look. Well, look. So I can take out the 5 and the 1.1 right off the bat. I can say that H itself is going to be equal to 5 over 1.1. Now, when I take this, crossed it, and I'll put the e to the minus j, and it's what? 3x minus 2y. Alright, so now when I have x cross z, it's what? Minus y, correct? So it's going to be minus 3 over square root of 13 ay. And when I have y cross z, ax, right? Positive. So it's going to be plus 2 over square root of 13, and it should be az. Wait a second. Ax, pardon me, ax. My bad. AX. Alright, and then if you want to multiply this out, 5 over 1.1 times 3 over square root of 3 and put a minus sign, that's the values. Did you take it that far?
Yeah, I think I made a mistake somewhere getting the eta.
Just tell me this. See if this answer is the degrees of 1%. Can you guys take this 5 over 1.1 times 3 over 13? Anybody?
Yeah,
What else? Huh?
that does.
It agrees? Alright, well, then if he was, yeah.
Yeah, well, can we go over how to get eta?
Alright, remember the definition of eta. The fundamental definition of eta is what? Square root of j omega mu over sigma plus j omega epsilon, right? Yeah. Alright, now hear me. Remember, it's lossless, right? We identify that because there's no e to the minus alpha z. See that?
Okay.
Alright, if it's lossless, I get rid of this term. Alright, now what happens? The j's and omega cancel, right? So then I get simply equal to the square root of mu over epsilon. That's how I got it.
Okay.
Now, I made an assumption, it was non-magnetic, he made the same assumption, so then I can take this and I can expand on it, I can say eta is equal to the square root of mu naught over epsilon naught times one over the square root of epsilon relative, alright?
Okay.
And the reason I can do that is because epsilon is epsilon relative epsilon naught, mu is mu relative mu naught, if it's non-magnetic, mu relative is one. Alright, now this I know is 125 over the square root of epsilon relative.
Okay, so we gotta find that epsilon relative first.
That's how I did it. Now Wentworth didn't do it that way. What Wentworth did, I think in his book, is simply take the curl of E and he divided by J omega mu, and he assumed it's non-magnetic. That's how he did it. I don't like curls. If I don't have to do them, I don't do them. Because then I have to put that big square thing, you know, do the matrix stuff. And especially when you get, well, you know, the curls you see are in Cartesian coordinates, right? When you get into spherical coordinates, or these other boloid spheroidal coordinates, there are 10 separable coordinate systems, they get extremely long and irritating. So I avoid them. That's my own personal thing. All right. So it agrees with this? All right. How many tried that problem? Just level with me. If you didn't, I understand, but please try to keep up. When I write that down, it's for a reason. These kind of problems get to be very tricky if you don't keep up with them. There's enough subtle problems about this one, they'll drive you nuts if you try to cram it and get it all in one night.
So in general, unless it's specifically stated, you can't just do free space. So he didn't say anything about that, and that was.
Now, you can assume it's lossless by looking at that and not seeing ether minus alpha z. You know it's lossless, right? So sigma is zero. But at that point, that's about it. Then you gotta go through and you gotta go. And the way I always get it, I get omega and beta, find the phase velocity. Hopefully, you'll be nice enough to say it's non-magnetic somewhere, and then you can get epsilon relative. This is the way I do this. And I always use that trick right there. Okay. Other problems from the homework. There were several I gave you, right? Yeah, yeah. This one will go a little slower. By the way, how would you get the wavelength for this? There's a couple ways. What is wavelength? You say it's 2 pi over beta, right? We got beta. That's one way. What's another way? Since it's lossless, what can we do? Phase velocity over f, right? We're not gonna, sure. So there's a couple ways, but those are the things that I ask on quizzes and tests. If you know your stuff, it's automatic. But if you don't know where to begin to ask questions to yourself, because you get real confused. I see that. All right. So we thought 619. Okay, go ahead.
As in seawater, a propagated electric field is given by E equals 20 e to the negative alpha z cosine of 2 pi times 10 to the 6 t minus beta z
Minus just beta?
minus beta z plus 1.5.
Oh,
Sorry.
plus 0.5.
It's AY volts per meter. This is assuming epsilon double prime is 0.
Okay, epsilon double prime 0, I like that.
Find alpha and beta and the instantaneous form of H.
And H, all right. Did they give you, they say anything about seawater? Conductivity is?
It just says seawater. It's in the air.
All right, so, give me the conductivity and the permittivity. I think epsilon relative is gonna be about 81. I think. And you check me on this, and then sigma, you gotta give me that. And you can't do these problems without these values, obviously.
Sigma is 5.
Is it 5?
Yeah, it's 5.
That's 5, 1 over ohmmeter, or Siemens meter.
Yeah.
Okay, and is epsilon relative 81?
It's
72.
So it
81
was,
is distilled water.
It's frequency dependent, but I like 81 because the square root, that's easy. All right, 72, we'll go with 72. So, how do we do this problem? Well, first, think of the fundamentals. What do we know that anytime you have any kind of problem, you know, at constant frequency, the propagation constant is alpha plus J beta, right? Now, we don't know if it's a good conductor or if it's a lossy dielectric at that frequency. They're asking us to find. So just do the whole 9 yards. That's the square root of J omega mu times sigma plus J omega epsilon. Y'all agree with that, class? Now I'll put the values in, and you punch them out in your calculator and give me the answer. So this is square root of J. Omega is what, guys? One look. Can you all see it? Yeah. This is omega, right? So it's going to be J times 2 pi times 10 to the 6th. And then it's going to be mu. It's non-magnetic, so it's times what? That's 4 pi times 10 to the minus 7th, right? Isn't that mu naught, guys? And that's Henry's per meter. It's that, then you have to multiply this by sigma, which is 5, plus J times omega, which is 2 pi times 10 to the 6th. And then it's got to be times epsilon relative epsilon naught, times 72, right? Times really 8.854 times 10 to the minus 12. And then I have to close the parentheses. So I'm going to get two numbers, alpha plus J beta here. Can you all do this for me? Boy.
Alpha should be 14.82 and beta should be 25.6.
25.1.
67.
All right, anybody confirm that? There's enough possibilities for errors. I'd like to get at least one confirmation.
Sorry, that was one problem. Should be 4.44.
All right.
For both of them.
All right, that sounds a little better.
That was 60.
4.44
Yes.
and plus J 4.44. Now, the minute you see alpha equal to beta, you know it's a good conductor. You all see that? But even before that, what we could do is this. We can compare sigma versus omega epsilon. Sigma is 5, isn't it? It's 5 down here. Omega is 2 pi times 10 to the 6th. Then it's epsilon, which is 72 times epsilon naught, which is going to be 8.854 times 10 to the minus 12. So just tell me what this amounts to right here. Wish I was better at this. So 8. Oh my gosh. That's like 0.008, I think, isn't it? 0.004. 0.004. Can you all see sigma is much, much greater than omega epsilon, so it's a good conductor. We could just, if it's a good conductor, you don't have to punch all those numbers out. You can just do what? Square root of J omega mu sigma. You could ignore the epsilon relative times omega. Y'all follow me on epsilon relative epsilon naught times omega? Because it is a good conductor. Do you agree with this, guys? How many students right here? It's a good problem. Now go ahead. What else for this one? We got alpha.
Beta and instantaneous voltage.
All right.
What's the units for those constants?
Well, alpha is Napier's per meter, and beta is radians per meter. But a Napier and a radian are kind of a fictitious thing. They're equated to each other. They have to be, if you add it together, they have to have the same units. And so it's Napier's per meter, or in this one, the beta is radians per meter. It's not degrees. Remember, it's radians per meter. Okay. And so how do we get the instantaneous form of H? We got this. I like to do this in a phasor domain. I recommend you do that too, so I'm going to do something here. I'm going to start there. And I'm going to put this in the phasor domain. Now, please, just for a second, think to yourself, what would the phasor domain form of this look like for the ether? Well, the magnitude's going to be the same. You agree with that? so it's 20. I'm not even gonna put the value of alpha in, I know it's 4.44. So I'm just gonna leave it as e to the minus alpha z. That's not a problem. Now, when I go to the phasor form, that omega vanishes, right? And what happens? Then I get e to the minus j beta z. I know beta's 4.44. And this is in radians, right? Right? So then I have to say it's e to the what? That's gonna be j 1/2 or 0.5. Do you all agree with that? Everybody follow me on this, class? Take a good look, make sure you see why I did what I did. I'm transferring this and putting it into the phasor form. Now I have this and it's in the y direction, right? Correct? Now, we want to take this and we want the value of h, correct? So, to get the back, I'm not going to take the curl. I don't know if he took the curl of this and divide by j minus j omega mu. What am I going to do? I'm going to calculate eta, right? So, looking at this, this is me personally. It's a good conductor. Do y'all agree with that, class? We proved that. So, if it's a good conductor, eta technically is what? Square root of j omega mu over sigma plus j omega epsilon, right? That's the technical definition. But being a good conductor, what can we do? Yeah, get rid of that stuff, right? So what we're going to see is, we're going to have square root of omega mu over sigma, and then the angle will be e to the j. It would be 45 degrees, but because we're going to keep it in radians, this would be what? Pi over 4, right? And because the square root of j is really equal to, I mean, j is e to the what? E to the j pi over 2. Square root of that is e to the j pi over 4. Okay. Now we have that, and that's in ohms, right? So, can you just tell me what this is? Omega is 2 pi times 10 to the 6. It's non-magnetic, right? So it's just times mu naught is 4 pi times 10 to the minus 7 divided by sigma is 5.
That uses J5
Alright, and look, this is a common problem. Engineers, it just doesn't ring sometimes in your mind true. If I have e to the j pi over 2, that is j. You all agree with that? Right? How many see that right there? That is the definition of j. Okay? Well, if I take the square root of this, it's the square root of j. Well, anything you take the square root of, what? You just multiply that by 1/2, correct, class? So that's e to the j pi over 2 divided by 2, or pi over 4. And if you wanted to expand that, it would be cosine of pi over 4, which is 1 over square root of 2, plus j sine of pi over 4, which is 1 over square root of 2. Or you could write it as 1 over the square root of 2 times 1 plus j. That's a completely acceptable way to do it too. I prefer to leave it like this right now, because we have another angle we have to add to that in a second. Y'all with me? Alright, now, by the way, there are no dumb questions. I find myself sometimes in the middle of a problem, I'm like, what in the world could that be? And it's like right in front of my face, but I didn't think about it for a second. Go ahead.
This is going back a little bit. Where did you get the 5 that you're comparing?
The what?
Where did you get 5 from where you're comparing?
The book, the conductivity, it's in a book as 5 for seawater. They provide that information.
Okay.
Woodward doesn't put in the problem, you have to look it up. It's his book, you can do what he wants. Alright. Now, back to this, you all see this, class? What's the value there? Pretty small. 1.2? Is that right? 1.2 or 1.25? Alright. And it's going to be e to the j pi over 4. So now, it's Beginski's way of doing it, not Wentworth's way. I'm not going to take a curl. What am I going to do? I'm going to say if I want h, we'll put it in the time domain, but I'm going to first do the phasor. What I'm going to do is take 1 over eta, unit vector, direction of propagation, cross into the E field. Y'all with me now? We got the E field, we got eta. By the way, what's the direction of propagation? Let's take a look. How many see it's z, right? And therefore, a unit vector in that direction would be az. You agree with me? All right, so now I come down here and I say that's 1 over eta, so it's 1 over don't forget the angle on this one, 1.25 e to the j pi over 4. It's 1 over eta times az crossed into the E field, there's the E field, 20 e to the minus alpha z e to the minus j beta z times e to the j 1/2, I wish it wasn't 1/2, but, and ay direction. So, do you all follow me? Just sticking it in to the actual equation defines the phasor domain. With me, everyone, class? All right, now, go here for a second and help me out here. If I take, well, let me do it here. As you've been working these problems, this stuff should just either confirm what you've suspected or really clear up any kind of misunderstanding. So coming up here, well, do me a favor, take 20 over 1.25, and what do you get? 16. All right, now, listen to me with these angles. I want you to hear me. When I take 1 over e to the j pi over 4, that's e to the minus j pi over 4. You all agree with that? So I'm just going to put that down there. This becomes e to the minus j pi over 4. Get rid of that. Y'all with me, class? Now, when I have that, and I have 1/2, what I really need to do is take 1/2 minus pi over 4 and give me that value. So it's e to the what? If I take 1/2 minus pi over 4, what do you get? Boy, that's negative, I think.
Negative 0.28.
Okay. E to the, so this is minus j 0.28 z, could have picked nicer numbers. Then, if you take a look at this, I'm going to have e to the minus alpha z times e to the minus j beta z. Both alpha and beta are 4.44. And what happens when I have az cross ay? Z cross y is minus ax, right? So I have minus ax, and that would be the phasor domain H field, correct? So to get it back into the time domain, remember alpha and beta, no, they're both 4.44, correct? So to get it back into the time domain, what do? Technically, I take this and I multiply it by e to the j omega t, right? And then I take the real part of that. But I know, and you know if you've been doing the problems, what I'm really going to do is simply bring that constant down. That's right here, this alpha strict real, so of e to the minus 4.44 z. That's all in front, right? Then I'll put the minus sign there, because that's minus ax. And I'll leave ax out here. Now, when I look inside the cosine argument, cosine of omega t, omega is 2 pi times 10 to the 6, minus beta, and beta is 4.44, right? Z, but there's this phase term, which is actually negative as well. So it's minus 0.287, and it's in the AX direction, and the units of this should be amps per meter, if it's the H field. And that should be the H field with time domain. Can anybody confirm that?
Yes.
Okay. Take a look at it. You asked it, you see what went on there? Most of the time, the things that cause you strife or some kind of concern is you're not sure a lot of times if you can get some of these quantities just by looking at this. Well, you can't. The only way you can get them is doing the calculation, getting gamma equal to alpha plus j beta. Yeah.
How come the e minus 4.44 is
Pardon me?
is outside the cosine?
Because that's what strict real, isn't it? You know, when we go from the phasor to the time domain, H field would be equal to the real part of e to the j omega t times H phasor, right? Well, the e to the minus 4.44 z is strict real, so it can come out in front. There's no imaginary term there. Are you with me on that? That's the reason you can do it. Okay, so I hope that answered your question. Any other questions? That's a good problem.
I have a quick question on 16, not to solve it, but we're given in this problem is medium where we had a really small inductance, 0.009.
Tell you what, let's talk about it so everybody can hear. Can you all hear back there? All right, let's do it.
Is given a conductance of 0.009 epsilon relative.
Oh, a sigma of 0.009, go ahead.
Epsilon relative is 1, and then mu relative is 100. I was just curious, what kind of material would that be?
Magnetic.
'Cause like,
It's magnetic. As a matter of fact, it's probably some sort of an iron. You know, when you use laminated iron for transformer cores, it's at a certain frequency, but that's,
but wouldn't that have a greater conductivity?
well, the thing is, well, the conductivity in pure iron is much, much greater, but you can add things to it to drop that conductivity to reduce the losses. You know what lamination is in your transformer cores and stuff like that? They do a whole lot of things to reduce eddy currents. Those are induced currents. And they also add things to iron to reduce the conductivity. And I am not a material science expert, and I don't know all the stuff they do, but I know these guys are bright, and they come up with ways of getting the best for the smallest amount of cost usually. But you're right, that conductivity is a lot smaller than anything made of metal that I know. All right, so what does it ask now?
So it was defined the instantaneous form of the electric field, but I was just curious about what type of material.
All right, by the way, with this information, just take a look at it. Do they give you a frequency?
They give you a 1 millimeter amplitude magnetic field and 100 megahertz.
All right, so they give you 100 megahertz. Now, knowing at 100 megahertz, right away you can figure out the value of omega times epsilon, right? And compare that to sigma. Y'all follow me? You can find out if it's a good conductor or not. And once you know if it is a good conductor, and I'm not sure it is, then you can go ahead and you can get the rest of the information straightforward if it is a good conductor. Did you do that, Bob? Is it a good conductor or not? Pardon?
Not really.
It isn't?
They're not very close.
So you have to do the whole 9 yards on this one. If you want me to do it, I'll do it. Did you do it?
Yes.
Was the answer right?
Yeah.
How many did that problem, out of curiosity? Couple people? No problems with the answer? Y'all got it? You good? You didn't do it? Honesty is the best policy. I'm never gonna scream at you for not doing stuff. I'm gonna encourage you to do stuff. I mean, you're paying for the course.
I forget what the difference was, but I think they're on the same order.
What?
The
I believe they are, but here's the wild one. See that mu relative? How is that gonna cause problems?
Magnetic field.
It's gonna also, yeah, and the value of eta is gonna be a lot different, because remember, eta is equal to the square root of j omega mu. Now that's mu naught times 100 over sigma plus j omega epsilon. Well, now all of a sudden, a square root of 100 is 10. That's 10 times what it would be if it was non-magnetic. That's significant, and that's probably the thing that causes your answer to look a little weird. Yeah.
So you have a good conductor if,
We don't know yet. I don't know.
well, if J omega epsilon is much greater than sigma.
If sigma is much greater than omega epsilon, then it's a good conductor.
Sigma is much greater.
Yeah, remember, this would have to dominate. If sigma is much greater, it's gotta be a good conductor. If omega epsilon is much greater, then it's a dielectric, a lossy dielectric at best.
What do you define as close, like same order of magnitude, or like?
Normally, it's power pin. So if you have sigma 10 times greater than the magnitude of omega epsilon, it's probably a conductor. You can usually ignore J omega. Unless you're talking about super precision stuff, but normally you don't do that.
Here we got beta is like twice alpha.
Well, no, alpha and beta, yeah, you can argue that if it's a very good conductor, beta and alpha should be the same. And if they're significantly different, then you can't really define one as it's not a great, it's not a very good conductor. It's both. It's a lossy conductor, or a lossy dielectric. Okay. You want me to do that one? If you guys did it, you got the right answers, there probably isn't a problem getting the right answers to this. But the curls are the one that will drive you nuts. So, that's the reason I avoid the curls. Okay. Let me go on with, what I wanted to do today. So I was, man, I've got 10 minutes. We're gonna do it. No, we're not. I want to talk about, first, we talked about propagation in good conductors, and I talked about something, just briefly alluded to skin depth. Do you all remember that class? So I said that in general, if we have an electric field and a pretty good conductor, we get this kind of behavior versus depth. If I take the magnitude of the E field on this axis, the actual value would be equal to sum E naught e to the minus alpha z. We forget the phase because we're talking about magnitude. So as you're at z equals 0, it's E naught, and it steadily goes down. It's going down at an exponential rate. And where it goes down, so the value of E naught times e to the minus 1, this is called the skin depth. And the way we get that is, well, I know that's alpha z, so alpha times the skin depth is 1. So really, this is simply 1 over alpha, and it's equal to 1 over the square root of pi f mu sigma. Now that's the skin depth. Don't forget that. This is a very important concept. This is for good conductors. So the next thing I always talk about is, well, what effect does this have on actual functionality of common things, like wires? Well, you know, if you have a wire, and we'll make it a round wire with a radius A, made of a material conductivity sigma of length L, and then I'm going to have my fictitious little battery here, and I have some voltage V, and a current flows through it, I can calculate the resistance. I'll just go through this one time by talking. I can say, well, I know if I's flowing there, I over the cross-sectional area, which is pi A squared, would be the current density J. And I know J is sigma E, so if I divide J by sigma, now I have the E field, and if I integrate the E field from here to here, now I get the voltage, and since I assumed I can take the voltage by the assumed I, and I get the resistance. Now you did that in EMAG 1. And you remember what you found, the resistance, and it would be DC resistance, for anything with a constant cross-sectional area, a wire, is always going to be proportional to 1 over the conductivity, then it's times the length, or L, capital L, and it's divided by the cross-sectional area. For this, since it's a round wire, it would be pi A squared. Y'all remember doing that? And that would be resistance in ohms. Now, if all of a sudden, we have an AC, not a battery, but an AC voltage there. And that causes the skin depth to be less than radius A. All right, y'all follow me on this? Now what happens is all that current is confined to one skin depth into the wire. So the profile of current looks like this. Here's one skin depth, right there, and all the current, you can assume, is confined to one skin depth down. I can do the whole thing for you where you actually get the profile of current into the wire and then do the integration, but mathematically, if the skin depth, right here, is less than the radius A, you can say it's all the current's confined to one skin depth. Now the area the current's flowing through is less than the whole area. Do you all agree with that? So this area that it's flowing through right here is going to be equal to pi A squared. Now that's the whole area, right? And then I subtract out this area. Well, that area has a radius of A minus the skin depth. So now I subtract out pi times A minus the skin depth squared. What you find out this comes to is going to be pi, right there. A squared minus A squared goes away. Then you're going to have 2A times the skin depth, because you're going to have these product terms here, 2 of them. But then there's going to be also minus delta squared in there. Now, I'm going to tell you one thing. I'm not going to do the math on this one because I'm trying to. But if you take a look at this, most of the time, this is not of consequence. Right? So what they actually do is they say it's approximately equal to just 2 pi A times the skin depth. Now let me show you something else about this that makes sense. This will help you with this one. If you think about this donut I got here and just break it at one point and flatten it out, then I would have this. I would have something that has a length that would be the circumference of this, which would be two pi, not times a. You know what I'm talking about, that's the circumference of a circle. 2 pi times a, and then the thickness of this would be 1 skin depth. So if I take 2 pi a times the skin depth, I get the area, and this is the cross-sectional area. What that means is, AC resistance, if the skin depth right here is less than A, is equal to, still 1 over sigma L, but now the area is about equal to 2 pi A times the skin depth. And that resistance, as the skin depth goes down and down and down and down, smaller and smaller, it goes up and up and up. And you can have a wire, a standard wire, that may have tenths of an ohm per meter of resistance, have all of a sudden 1,000 ohms of resistance at, say, gigahertz. Y'all follow me? That's why it's so important, especially these high frequency applications. You won't see solid wire. What you'll see is these small little pieces of wire, and tons of them that are woven together. They've got some kind of insulation they'll weave them, because now all that current rides on the skins of those wires, and they don't care about the inner part of it. And you won't get like one. You know what I'm talking about? Braided wire will have hundreds, maybe thousands of actual slivers of wire there that are wound together. That also, there's a lot of reasons for that, not just one. Okay, you with me on that, guys? So, I'll give you some problems that you calculate the resistance for different types of geometries, but fundamentally, the only thing you're doing is going to eliminate, you're going to see, first of all, if the skin depth is important. In other words, if it's small compared to the radius, and if it is, then you have to find the reduced area the current's flowing through. And remember, anytime you have wire that is driving a signal differentially, like a standard communication channel, you have current going this way and returning in the opposite direction at the same time, you have to get the resistance of the top and add it to the resistance of the bottom per meter. Y'all follow me on that, class? Okay, just remember that. All right, now power. That's the one thing I was going to do today. I'm going to get through this. I have 5 minutes, I think, or less. So, I mentioned some things about this, but I'm just going to get right to the point. When we talk about power in general, you're used to seeing voltage multiplied by current to give you power, right? Instantaneous power. Well, if you want to talk about the instantaneous power flow, and it's a vector term. Technically, it's going to be E instantaneous of T. It's a function of Z too and stuff, but crossed into H. That's instantaneous. We don't really care about that much. Some people might. If you're in high energy physics or you're doing some transient problems, you do it this way. But the way we normally do it is we take a look at the average power, just like you took a look at average power, right? You had real power and you had what? Reactive power. How many had power? Do y'all have it? Right. Well, the real power is the thing you care about for dissipation, right? And normally speaking, when we talk about propagating waves and stuff like this, we talk about the average power. It's a vector, and it's equal to 1/2 the real part of E cross H conjugated. Now, these are phasor terms. E and H here are phasors. So I'm going to just take you through this in a way that should make sense to you. I'm not trying to fly through this, but follow. I'm going to keep with Whitworth's his convention. We're assuming it's propagating in the Z direction, and it has an X orientation for the E field. So if my E field in general is given as some E naught times e to the minus alpha z times e to the minus j beta z, and it's in the AX direction, then the actual H field that would come for this, right? We can go ahead and take 1 over eta times unit vector in direction of propagation crossed into the E field. But we've done this several times already. The H field that's going to come out of this is going to be E naught over the magnitude of eta. Now the angle is interesting because it's going to be e to the minus j, whatever this angle is, on eta, but it's got a minus because it was downstairs, I brought it upstairs, so it's going to be minus that angle. Do you all follow me, class? What I'm doing here? All right, then it's going to be times e to the minus alpha z e to the minus j beta z in the AY direction. You can check me on this, we've done it at least twice, we've done the same thing. This is the H field that would result from a E field propagating in the Z direction, oriented in the X. Y'all remember this? Now when I take a look at this, right here, and I apply this field, this magnetic field, into this equation, I end up getting 1/2 the real part of E, well there's E right there, so it's E times e to the minus alpha z, e to the minus j beta z, in the AX direction. It's crossed into the H field, but it's the H field conjugated. Now, the E naught magnitude of eta, is not affected by it, so I have E naught over magnitude of eta. That angle changes, now it becomes e to the positive j theta n. That's not affected. E to the minus alpha z stays the same. This changes sign, it becomes e to the positive j beta z, and it's in the AY direction. And again, the only thing I've done there is take these and put them in there with conjugation on the H field. Now following on this last part, and then we're about done. All right, can you all see how I have E here, and E naught here, and E naught here, and eta? They're all real, and they just multiply each other. So I can take 1/2 magnitude of E naught squared over magnitude of eta comes out. Then I have e to the minus alpha z here, and e to the minus alpha z here. So it's e to the minus 2 alpha z. You all see that, class? So that comes out. So I have e to the minus 2 alpha z. Then, and this is the important part, e to the minus j beta z times e to the plus j beta z. What is that? E to the 0 or 1. You all follow me on that? So actually, cancel is a good way. We're going to cancel that. Finally, I have to take the real part of e to the j theta n. Well, think about that. E to the j theta n is cosine of theta n plus j sine of theta n, right? The real part would just be the cosine. You follow me? So that means it's times cosine of theta n, and then it's going to be, if you look at this, what's ax crossed ay? Az. And that is the power in watts per meter squared. It's the average power, PF. Sometimes you'll see this called a pointing vector, and you'll see the symbol S for it like that in the real world.
The average power vector is pointing vector.
Well, they'll use pointing vector for average or for instantaneous. If it was instantaneous, it'd be a function of t. Average power is not a function of t. Right there.
For the phasor form of the magnetic field, why did it go from negative j beta z to positive j beta z?
Conjugation. You know conjugation is? Okay. All right, guys, I'll see you on Wednesday.
You just take a negative off of every time.
Conjugation is find out a plus j, all that. Yeah, by the same token, you have a equals some magnitude of a equals j. Right. Conjugation is common. I still got that.